Segmented trees. What are they and why do we need them? So basically in general, we have problems that we want to solve. Let's not think for a moment about the wording segmented. We have problems that we want to solve. So we have some kind of an input. In our program, we'll do some processing and then we'll have the output. Segmented trees deal with ranges. Because you see, when we have the specific question of ranges, then we need to scan some items in order to do an operation on a range. For example, if you ask how much rain did we get on multiple days, then you will need to ask how many rain did we get on day 1, on day 2, and day 3. And if you ask again, then you need to again go over the days and get the range, and each some time it's like an O of n on the worst case, because in each time you would need to go over the whole of the array and to ask again how much rain did we have on this range. So the specific case of ranges is not a question that we ask on a specific item on an array. It's not on a specific item on an array. It's on a range of items on an array. So when we have such queries that deal with ranges, then maybe we need some better data structure in order to handle this. And this is the segmented trees. This means that we are going to take a data, in a data structure, a simple one, such as this array. Let's say that we have this array, and on each day, let's say that we have index 0, index 1, index 2, index 3, index 4, index 5, index 6, index 7, and index 7. 8 cells, power of 2, and on each day we had some kind of rain. On day 1 we had 0 millimeters of rain, on day 2 we had 2, and day 6 millimeters, 8 millimeters. On each day we had different millimeters of rain. And then we ask on a range. But remember, it's not that we ask on the range only one time, where we need to go over the indexes, we ask many times. So this is going to optimize for many queries. We want to get many queries results in a more efficient way than scanning the whole array. So how are we going to do this? So we're going to create a different data structure. What other data structures do you know? Trees. Okay, so in this new data structure, the way we are going to build it is to utilize the fact that in trees we have log of n in order to move from the parent to the child, right? So this is log of n, and we are going to use this feature. So we're going to build a full tree where all the array items are only the leaves. So if we had here 2 millimeter, it's going to be here. If we had 1 millimeter, it's only going to be on the leaves. And why do we need all the nodes inside the tree? We know we need them in order to store sum. So a node in the tree would be the sum of the millimeters of rain that it go to the children. This is called augmentation, because we are going to augment the tree with some feature of the leaves. In this case it's sum, but it could be the median of the leaves, and each such parent on the tree would contain some augmentation on its children. And in this way, when we ask, if we ask on a range of nodes 0, 1, 2, 2 and 3, then we don't need to scan the tree from the root to the leaves, because we are going to see that we are going to have a node inside the tree that would already contain the sum, so we would stop there. Okay, so this is going to be very good for sums, for ranges over items. So now there are two questions. How do we build this tree? and how do we extract data, the queries, the query side. In order to build the tree, step 1, build the tree. Step 2, query. In order to build the tree, we know what are the indexes, okay? So we know this is going to be index 0, this is going to be index 1 from the array, and all the leaves are going to have their same indexes. So we have all the values of the rain. Okay, if we had here 3 millimeters, 4 millimeters, so all the values are now on the leaves of the tree. And now we start asking questions, because let's say that we had here 3 millimeters, 0 millimeters, 0 millimeter, 1 millimeter on the leaves, 2 millimeter, 3 millimeter, 4 millimeter, and 1 millimeter. So we know that the sum, the parent here on the sum would contain here 5 millimeters, and another parent, we just sum the leaves. We are going to have here also 5 millimeters, and over here it's going to be 3 millimeters, and over here it's going to be 1 millimeter, and we move from the leaves, and you see we are building this. We are building the segmented tree. So it's enough for you to be here and to build the segmented tree up to the top. And now it's only technicalities. How do you build a tree from the bottom to the top? And here we have 14. So we know that the sum of the whole array is at the root, and it's going to be 14. And this is the buildup of the tree. How can we possibly build it? We can take an array. We can utilize the fact that we know that the leaves of each leaf of each node on a tree, this is some kind of trick, is for index I, the left child is going to be 2i plus 1, and the right child is going to be 2i plus 2. Okay, so with this we can build a tree, because if we are at some kind of index, we can find the root of them. And now we have the other case where we need to do the query. In the query, we start from the root. So what is the range of the root? Let's say that we need to query these children here, which are indexes 2, 3, and 4. Let's say that we need to query the range 2 to 4. So we look at the root. What is the root representing? We already know. The root is going to 0 to 7. This is the root. We know this. You don't need to tell me, because we know that the leaves are 0 to 7, 0 to 7 indexes. So we know that the root represents the whole range. So if someone asks you, after you build this tree, what is the range sum of 0 to 7, you will stop at the root, because you say, oh, this is 0 to 7, I already know this. But what if someone asks you about 2 to 4? Okay, so we say, 2 to 4. So I look here, I know that I'm 0 to 7. What would be the left tree? The left tree, I know this. It's going to be the half of this range. It's going to be 0 to 3. I know this. You don't need to tell me. And what is going to be the left side? I know this. It's going to be 4, 2. So when you do the recursion, you can already know this. It's going to be 4 to 7. So what did you ask me? 2 to 4. 2 to 4, I don't see it's fully included here. It's actually going to be fully included here and partially included here. So we need to go to the actual child, to here. Okay, so 0 to 3. What are the left and the right child of 0 to 3? I know this. It's going to be 0 to 1. And you see, we don't need to get to the children to know that the range covered by the node which covers 0 to 3, the left side is 0 to 1, and the right side is 2 to 3. So 0 to 1 doesn't do anything. We stop here. Doesn't do anything for us. 0, but 2, the range 2 to 3 that we know that we have here is fully included in 2 to 4. So we can already return one Okay, and we don't need to get to the actual children. So we finished with this, and now you go with the recursion to here. We know that we have 4 to 7. 4 to 7, do we need this? Yes, but it's not fully included. 4 to 7 is not fully included here, so we continue to the left and to the right with recursion. So here we have 4 to 7. If we had 4 to 7, then the left child would cover 4 to 5, and the right child would cover 4 to 7, and the right child would cover 6 to 7. 6 to 7, do we need this? No, it's outside the bound. 4 to 5, yes, but it's not fully included here, so we continue to the left and to the right, and now we have 4 to 4. 4 to 4 fully included. And to the right child, we have 5 to 5 not included, and we finished. It's 1 plus 4. We know that sum is 1 plus 4. Okay, so you see, we build, this is it. This is the segmented trees. The segmented trees means we had a data structure that was useful for getting specific items. We know specifically how many millimeters of range we had at the index 2. But now we need to move into a data structure that would contain ranges. The ranges could be sum, augmented tree, sum, it could be median, it could be whatever, okay, whatever function that is dependent on the children. And when we say that we have function that is dependent on the children, we think recursion. And then we know exactly that the root would contain all the nodes, all the sum, if it was the function. And when we build a tree, very easily from the bottom to the up. And we first built and calculated all the sums. And now each time we need to do a query, we already know what are the ranges. The root node is the whole range, 0 to 7. The left node of the root would be half of the range, the first half, 0 to 3. The right range would be 4 to 7. And whenever we have a range that is already included in the original query that we needed, we add it to the result. So this was a brief introduction into segmented trees. I hope you enjoyed this. I surely did. Let me know what you think, and see you guys next time.